Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali.
Thank you very much. I'm Philip Emeagwali. In 1989, I was in the news headlines for discovering that practical parallel processing will become the vital technology that will underpin every supercomputer. Parallel processing changed the way supercomputer scientists compute. Before my discovery of practical parallel processing that occurred on the 4th of July 1989 in Los Alamos, New Mexico, United States, the vector processing supercomputer market was only $1 billion a year and had 25,000 scientists programming those supercomputers. Before that discovery, the parallel processing supercomputer market was a few $1 million a year, and I, Philip Emeagwali, was the only full-time programmer of the most massively parallel supercomputer ever constructed. Today, the vector processing supercomputer market has vanished, and the parallel supercomputer market has grown to $20 billion a year. Each dollar that was spent to purchase a supercomputer was a vote of confidence on the massively parallel supercomputer that was mocked in the 1980s as a huge waste of everybody's time. Parallel processing changed the way computer scientists thought about the computer. My contributions to extreme-scale parallel processed petroleum reservoir simulation was the cover story of the May 1990 issue of the Siam News. The Siam News is the news journal that is the mathematician's equivalence of the Wall Street Journal. My contributions to petroleum reservoir simulation changed the way computational geophysicists search for and recover crude oil and natural gas. Computational geophysicists paradigm shifted from low fidelity simulating with only one processor to high fidelity simulating across an ensemble of processors. My contribution to scientific knowledge makes it possible to construct extreme-scale models and high-fidelity simulations that can sift through millions upon millions of complex mathematical variables and help researchers to answer the biggest questions arising in science, engineering, medicine, and business. That contribution to extreme-scale computational physics is the reason my discovery of practical parallel processing was highlighted in the June 20, 1990 issue of the Wall Street Journal. Why is it that 1 in 10 supercomputers are purchased by the petroleum industry? My short answer is that although the fastest supercomputer costs $1.25 billion, that supercomputer saves the petroleum industry money and do so because it will enable the industry to discover and recover otherwise elusive crude oil and natural gas. For instance, it costs up to $10 million to drill a new oil well onshore in the Niger Delta region of southeastern Nigeria. And it cost up to $100 million to drill a new oil well offshore of the Atlantic Ocean coast of Nigeria. So if the new well finds no crude oil or natural gas, then $10 or $100 million is lost. The parallel processed, extreme scaled, and full field simulations of the oil fields of the Niger Delta region of Nigeria helps make informed decisions about where to drill for crude oil and natural gas, and helps improve the success rate. Parallel processing, the technology that was mocked and made fun of back in the 1980s, is the reason 1 in 10 supercomputers are purchased by the petroleum industry. The parallel supercomputer is the 21st century's divining rod that must be used to pinpoint new deposits of crude oil and natural gas, such as the new South Africa's first deep water oil discovery and the new oil finds along the West African coast of Liberia, Sierra Leone, and Senegal. Parallel processing changed the way computational geophysicists find new deposits of crude oil and natural gas. The parallel processed high fidelity, extreme scaled reservoir simulation is used to determine a priori the amount and locations of the crude oil and natural gas that are buried a mile deep inside an oil field that is the size of a town. In parallel processed petroleum reservoir simulations, the 3 conservation laws encoded into calculus are those corresponding to the conservation of momentum, mass, and energy. To parallel process, the oil field that is 1 mile deep and the size of a town is chopped up into 10 million small cells. Each cell is a 3-dimensional cube. Each cell is assigned to 1 processor. Each cell has several physical properties such as pressure, temperature, fluid velocities for oil, water, and gas, the relative concentration of oil, water, and gas, and so forth. On July 4, 1989, I discovered how to push the boundaries of supercomputing and push them forward while solving the toughest problems in the world, namely, simulate the flow of crude oil, natural gas, and injected water flowing across an oil field that is 1 mile deep and the size of a town. Oil fields have been operated since 1860. However, the earliest ideas about mathematically modeling production oil fields began in the 1930s, a decade before the programmable computer was invented. In the 1950s, the use of supercomputers to simulate the flow of crude oil flowing across a production oil field allowed petroleum geologists to model oil fields that has non-uniform properties and allowed computational geophysicists to incorporate the problem domains of the arising initial boundary value problems that had arbitrary shapes and allowed computational mathematicians to formulate the system of coupled, time-dependent, and 3-dimensional governing partial differential equations with nonlinearities. Partial differential equations with such complex properties cannot have analytical solutions. When no analytical solution exists, the nonlinear partial differential equation must be discretized as the precondition to parallel processing the arising system of equations of algebra and doing so across an ensemble of millions upon millions of commodity off-the-shelf processors that are tightly coupled to each other and that share nothing between each other, and that solves that grand challenge problem as one virtual supercomputer. The parallel processed petroleum reservoir simulation yields enormous resolution and clarity, and do both while reducing the time to solution and reducing the risk associated with the exploration for crude oil and natural gas. The holy grail in parallel processing is to figure out how to reduce the size of the supercomputer and reduce it from occupying the space of a football field to the space of a ping pong table.
Insightful and brilliant lecture.